So we were talking yesterday, we did that interesting problem about the wire, right? And we found that the way to maximize enclosed area was just to do a circle, right? All circle. So this is kind of a fun thing to look at here. If you look at, this is just another fun way to kind of have a little fun with Desmos graphing. So if we want to look at the areas of fixed perimeter regular n-gons. So what does that mean? What's a regular n-gon? Think back to geometry. This is just from last year. Well, yeah, what kind of shape? So what's an n-gon? Yeah, a shape with, right? It's just going to be a two-dimensional figure with n sides, and if it's a regular n-gon, what does that mean? All the sides are congruent, and all of the interior angles are going to be congruent, right? So what's a regular 4-gon? Square. What's a regular 5-gon? Yeah, a pentagon, right? Okay, and so on. So the areas, what's a fixed perimeter regular n-gon? Yeah, so the perimeter would be some constant, right? So let's look at this then. So I just built this little Desmos document here to demonstrate something. So we're going to let the perimeter equal 10. And we're just looking at what the areas would be based on the number of sides of a regular n-gon with a perimeter of 10. So what do you notice if you look at this graph? So along the x-axis, you'd see the number of sides. The area of a regular 2-gon is what? 0. Of course, it's 0, right? Because it's not, everybody get that would be one-dimensional? Okay, but when you get to a regular 3-gon, well, that's just what? What kind of triangle? Equilateral triangle with a perimeter of 10 would have an area of about 4.8, right? And a regular 10-gon would have an area of about pushing 7.7 and so on. Well, what do you notice about these graphs as you start to get up towards higher numbers? Yeah, you can see that the algorithm kind of falls apart when you when you get into values of n that are less than 1, which doesn't really make any geometric sense, right? So really what I probably should do here with this, and you guys probably noticed this and were wondering what the heck was Mr. Roya doing. You probably I should have done this. F of x equals, and we would just do a function where we'd limit the domain, right? So we'd say x has to be greater than or equal to 3, how about? And that would be a little better, wouldn't it? Okay. What do you notice as the number of sides gets really, really big? Yeah, it approaches, looks like it approaches some horizontal asymptote, right? What do you suppose the value of that horizontal asymptote would be? Can you tell me what number, what area we want? I want to know what that, and then we'll graph it so we can just show that it does have a horizontal asymptote. So, okay, yeah, so let's figure this out. So it'd be what? I probably should have picked, well, I mean, it's pretty hard to pick a number that's going to be compatible, but how would we figure out what the area would be? Okay, so area of a circle with a circumference of 10. Yeah, exactly. Right, so we would just be doing something like this. Circumference equals, what's circumference? 2 pi r. Come on now, you guys are awake, right? And if that equals 10, what do we need to know? If we want to calculate the area of that circle, what do we need? We need r, yeah. So r would just equal 10 over 2 pi, which is the same as 5 over pi, right? Okay, so then area would just be pi r squared, so that's pi times 5 over pi quantity squared. What am I going to get? 25 over pi. Okay, that's the area of a circle of circumference 10, right? Okay, so let's go back and let's just, how about if we graph the horizontal line, y equals 25 divided by pi. And let's make it red, how about? Okay, that works, doesn't it? Right? If we zoom in, we can see that sure enough, we're approaching that asymptote, aren't we? And let's everybody agree? We're just gradually approaching that asymptote. Okay. So a circle you could actually consider to be what kind of a regular n-gon? Yeah. It's equivalent to a regular infinigon is a circle. Yeah. Okay.
Did we finish our talk about animal history?
I mean, I think we kind of did. Yeah, right. So we said, I mean, we were just talking about how the bigger a circle, the more efficiently it encompasses area, right? And so if you just expand that to 3D, you'd get spheres. And so bigger animals that are in cold environments that have to limit the heat loss through their skin would have to be pretty bulbous, and they are. In whales, walruses, etc. And then the other part doesn't work quite as well. But if you think about it, you'd want to, if you're a warm-blooded animal and you're living in a really hot environment, your big problem is cooling yourself. Where do you cool yourself? You know, through your skin. And so you'd want to have the opposite going on. You'd want to have lots of surface area, inefficient, right? You want to be inefficient in your encapsulation of volume, right? You'd want to have lots of surface area for your volume. And so animals would tend to be smaller. They'd tend to be not very spherical, right? They tend to be kind of more angular. And they are. That's if you look at animals that live in really hot deserts, they're typically really small mammals. Or they're animals that, like an elephant, we said it's a big cheater because it's got radiators on its head. Hippos live in the water, so they cool themselves in the water. That's no big deal. But the other animals are all pretty, I mean, they're not real big and bulbous, right? They take a different approach. So that was our talk. All right, so now we better do something. So how about this? A capsule-shaped industrial pressure tank formed by adjoining two hemispheres to the ends of a right circular cylinder. So do you see that's what we have there? Like if you look at those big industrial tanks, like a propane tank or something, or if you look at the tanks on the back of a truck, don't they just kind of look like that, sort of pill-shaped? Okay, I mean, there's a reason for that, right? They're easy to make, and they're good at withstanding high pressures, interior pressures. This one it must have a volume of 4,000 cubic feet. The hemispherical ends cost twice as much per square foot of surface area as the cylindrical sides because they're harder to produce, presumably, right? So we're supposed to find the dimensions that will minimize cost. How are we going to do that? Is minimizing cost in this case the same thing as minimizing surface area? Is it? How come?
Because the hemispherical ends cost costs twice as much per square foot.
Okay, so yeah, so parts of the surface are weighted, right? It's kind of like, in this case, cost is sort of like a weighted surface area. Everybody get that? You understand when I say the word weighted there, do you understand what that means? Like when you weight something, you're giving it, you're multiplying it by some coefficient, right? Like if you talk about a weighted grade, for example, in a class, what's that mean? Well, it means a weighted grade on a transcript means that you're multiplying your GPA by some coefficient to give it more value if it's an honors class, for example, right? So in an honors class, it goes up to 5 points instead of 4 points, right? So really, you're multiplying by 5/4. You're multiplying your GPA by 5/4. Or you're just adding one to it, I guess, what you're really doing. But everybody get that? When you're weighting grades, if you use weighted grades, like in our grading policy for you guys in this class, assessments are 90% of your grade and homework's only 10% of your grade. So if I grade everything based on a 100-point assignment. So what would I be multiplying? I mean, is a test grade of 100% the same as a homework grade of 100% in here? Well, obviously not, right? How come? Not weighted the same. It's weighted, it's got 10 times more weight than a homework grade, right? Your average grade, and we have way more homework assignments, and so those even become less important, each individual one. You get the idea though, right? So we've got a cost in this case is a weighted surface area. Now, if the costs were uniform for the end caps and kind of the lateral, the barrel of this thing, then we could say, yeah, cost is just proportional to surface area, and we could just minimize surface area. But that's not going to work here, is it? Right? So what should I do? What do you think?
Could you multiply the spherical and the coefficient of weight?
Okay, and then the lateral area by 1? Okay, I mean, everybody get that? That's a pretty good idea. See if anybody can poke a small hole in that, though. Before we do that, though, let's look at the area component, right? If we're going to call, how about the width of the cylindrical part of the tank, we'll call that X, and we'll just call the radius of the hemispherical caps and the cylinder, just call that R, how about? So let's draw that on here. So this distance from there up to there is R. Okay, then what's the combined area of the two caps? One full sphere, yeah, right? And what's the area of a sphere of radius R? Surface area. You probably want to get familiar with these simple geometric formulas that you use constantly. 4 pi r squared, there it is. So that's going to be the area of the end caps. And what's the area of the cylinder, of that lateral surface area of that cylinder, that hollow cylinder? How do you get that? Rather than memorizing it, just visualize it. Then you won't ever forget it. How do you get the area of that tube?
Would be the perimeter area of the circle.
Okay, so that's one way to do it. The area, the circumference of the circle times the length, right? So that's one way to think about it. If I took a hoop with a circumference of 2 pi r, right, and I just extruded that through space by some distance x, then I'm going to sort of create a surface area of the circumference times x, right? Okay, the other way to think about it is, what if I just took this thing and cut it and unrolled it? What shape would it make? Rectangle, good. The width of the rectangle is just x. What would the unraveled or unrolled length of the rectangle be? Yeah, it'd be the circumference, 2 pi r, right? So either way, I just get 2 pi r x. Okay, so now the question becomes, what do we do here, right? How do we weight these things? So that's not a bad idea. Aiden suggested we multiply 2 times the end caps and 1 times the cylinder. Okay, what's wrong with that though? What does that assume? Say it again? Yeah, so if we just multiplied, like if we just did this, if we just multiplied 1 times that area plus 2 times that area and made this cost. Well, they may or may not be the same surface area, but what does that 1 and that 2 really mean? Like what should the units of cost be? Like, I mean, the most simplest units we could come up with for cost in this case would be what? Would be what? Dollars, right? Right? And so what would the units of that 2, for example, have to be? $2, but if I want my answer to be in units of dollars, because it's a cost, it's got to be $2, it's got to be kind of a you know, like a rate. Right? $2 per what? Per square foot, wouldn't it? Because what are the units of 4 pi r squared going to be? Square feet, right? Because we're talking about feet in this, right? So I would have to, in order to come up with dollars, I would have to cancel the square feet and replace it with dollars. Everybody see that? So really what that 2 is really saying is $2 per square foot times the number of square feet, right? Everybody agree? Okay, but do we know that that's the cost per unit area of the end caps? Does it tell us that they're $2 per square foot? It doesn't. I mean, they might be $200 per square foot. We don't know. So just arbitrarily picking 2 and 1, that's going to be $1 per square foot, right? That assumes something we don't know. And we're going to get an answer, we're going to get a specific answer in terms of dollars that's unlikely to be correct. So what would we have to do instead? Because they don't tell us what the cost per unit area. Does that make sense when I say that, cost per unit area? What I mean by that? Cost per unit area means how many dollars per area measured in something. Square feet, square meters, right? Whatever, right? Whatever, however we would express that. In this case, it's per square feet. We don't know what the cost per unit area is. So how could we deal with that? What could we call, for example, the cost per unit area for the cylinder? I'll give you a hint. We may not be able to, we don't know an exact value, right? So we can't put a number down. Okay, it'd be a variable, but it wouldn't actually be, it's not really a variable in this case. And I'm being super nitpicky here, but I want you guys to make sure you get this terminology right. It's not a variable because it doesn't vary in the context of the problem. It'd be a constant. Right? It's really what we'd call in math a parameter. It's something that's a constant, but if we adjust the parameter, it's going to change the overall cost. So it sort of acts like a variable a little bit. But in the context of this problem, the costs are fixed, right? Maybe it's 15, I don't know. Maybe the cost per unit area for the cylinder is 15. I'm just arbitrarily saying that. If it's 15, then as we tweak the dimensions of this cylinder, it's going to change the overall cost. But the $15 per square foot, if that's what it is going to be something that's fixed during this problem. Everybody get that? Whereas the X and the R are variables. Those are going to change in the context of this problem because we're trying to pick what are the dimensions that are going to give us that total volume that are going to minimize cost. And so in that process, I'm going to be kind of, like squeezing this pill so it becomes shorter and and thicker, right? So it's got a bigger radius, or we could extend it out so it's got a smaller radius and it's a longer pill shape, right? Those are things that we need to be able to vary to find the optimum result. But the cost per unit area is something that's going to be fixed within the scope of doing this one problem, right? So it's got to be a constant or a parameter that we're going to set. So let's just call it something. Usually we just use something like K. We reserve like X's and Y's and Z's and W's. Those are variables. And then other things like, for example, K's and M's and N's and those kinds of things we usually reserve to be constants or parameters. So we'll call it we're going to call it K. K is going to be the cost per unit area for the cheap part. So the cost per unit area for the more expensive caps would have to be double that. So it's 2K. Do you see why this is better? Because now we haven't fixed what our answer is going to be in terms of K, which we don't know. It's not given to us. Give me 1 to 5 on that. You see the difference? It's a subtle difference, but it's really important. Okay, so now we can just do calculus. Now we've got a cost function. There's our objective function, right? What's the problem with this? 2 variables, yeah. So I'm going to need some secondary equation, right? Okay, it's got to come from some number. What's the constraint on this? We can't just make this thing 0 size because it has to enclose that much volume, right? So what's the volume going to be? How would I calculate? And you guys can just figure this out. What's the volume of that shape going to be? Break it into pieces, right? The 2 end caps combined create what again? A sphere. What's the volume of a sphere of radius r? What is it again? Well, that's an area. Almost. 4/3 pi r cubed. Again, you just kind of want to just gradually, as you do some problems, you'll just remember these, but you do want to know those. Those are things you'll see quite a bit. So that's the end caps. How about the volume of the cylinder? What's the volume of a right circular cylinder? So a cylinder that's got it's got a circular base, and the height is perpendicular to the table that it sits on. Pi r squared times x. Yeah, you just multiply the cross-sectional area times the length that area is being extruded through to create the space or the volume. Okay, so there's our volume equation. Okay, now we got to be smart about this. Right, we've got to eliminate a variable. That's our equation of constraint or our secondary equation. We're going to solve and substitute, but there's definitely a much easier way to do this. Which variable do we want to solve for and substitute? I totally agree, x. What's the really compelling reason it's got to be x? It's only one factor in the secondary equation and in the objective function. Right? Everybody see that? R would be a really bad choice because we'd have to, first of all, it'd be really tough to solve for R. And even if we did, when I'm substituting R, I've got an R term and an R squared term. So again, that'd be really, really, really tough and totally unnecessary, right? So we want to solve for x, which is easy to do. Just going to subtract that term and divide by pi r squared. And so what do I get if I do that? How about if I clear fractions? So we multiply the 3 all the way through. We subtract that term to the other side, and we divide by 3 pi r squared. And there's x, right? So that's what I'm going to substitute. Okay, I'll just plug that in there, right? Where I had an x, I'm going to substitute that expression. Okay, now what would I do? Just a lot of algebra. I want you guys to kind of talk me through this. What would I do? Yeah, just distribute that, right? So if I distribute that, I'm just going to get that, right? When I distribute to this first term, I can cancel quite a bit. I could cancel the pi's, I could cancel an r, and on the top I just get 24,000 k over 3r. When I distribute over here, again, I could cancel a pi and an r, and I get that. Okay? Okay, now what?
Simplify it first.
Okay, so I could reduce that one, couldn't I? Yeah. And what else could I do? I guess I didn't mention it, but what else could I do? Yeah, I could factor out the k, right? As far as the calculus is concerned, is k a variable or a constant? Constant. What's the only variable when we're taking a derivative here? Because we're going to have to do some differentiation. What's the only variable of differentiation? R. Yeah, right? Everything else is a constant. So the k is a constant. We can just pull that out front and leave it there, right? Okay, so what do we get then? If we simplified this and we combined these like terms, we got that. I guess we didn't even simplify that yet, right? Oh, and that k shouldn't be there, should it? Whoops. That's not supposed to be there. Either is that. Those k's all got pulled out front. Okay? Come on.
Why would it be 16 pi r squared? Didn't we have to make the common denominator?
You do. So I'd multiply by 3 over 3 and I'd get, that's a negative. Yeah. Everybody get that? I mean, it's the individual, like the algebra, you could all do this algebra. I don't want to get too bogged down in the algebra. We just got a common denominator and combined that stuff is all we did. Okay. Okay, so then we could factor out a 3 from the denominator, and we could factor out a 16 from the numerator. And then we're starting to get something a little better then when we get this thing factored down, right? That 16/3 k out front can just stay there. And now what? So we got our function. Okay. We need the domain, yeah. Good, we need the domain. Did I include that? No, I didn't even bother. So we need the domain. I forgot that. Let's do that. What's the domain going to be in this case? And remember, it's always good to look back at this thing, right? You want to look back at the substitution equation where you've solved for the other variable. The domain's in terms of r. So what's the bottom end of our domain? 0. Can we include 0? How come? Matthew, how come? You're right.
Is it because like the 4 pi r cubed would go to 0 back into the bottom?
No. No, but what's the problem here? If x, which is the length of that tube, is equal to that expression, there's a red flag in that expression. Why can't r be 0? Yeah, because look, there's an r in the denominator, right? And you can't divide by 0, so we can't include 0, right? As r goes to 0, that's going to mean that x is going to get super, right? It's going to get super long, okay? What's going on with, everybody see that? Right? As r goes to 0, that term's going to disappear. But as the bottom disappears, that fraction, that 12,000 on top just stays there. And so the fraction's going to go to infinity, right? You can see that this thing would just get really distended. Okay, so there's the lower end of our domain. What's the upper end going to be? this is going to be kind of a weird one. Because what's the smallest x could be? Yeah, if x is 0, then what would happen to our shape? No, if x goes to 0. What would that make it, though? What kind of shape? If x goes to 0, it'd just be a sphere, wouldn't it? Right? Because the tube would just disappear. It'd just become a sphere. And so all the volume would be contained in that sphere. Well, what's going to happen if x goes to 0, what's the condition we can take away from that equation? What's going to make that fraction go to 0? If the numerator goes to 0, right? Everybody see that? Okay, so we could say then when x equals 0, the top would have to be 0, so that would mean that 4 pi r cubed would have to equal 12,000, right? And we would just solve for r. Divide by 4 pi. So r cubed would just equal 3,000 divided by pi. Everybody agree? The 12,000 over 4 just becomes a 3,000. They get a pi on the bottom. So r would just equal the cube root of that, whatever number that is. The cube root of 3,000 over pi. Somebody real quick, crank that out. What is that roughly? It's about 1,000. It could be a little over 10 point something. Real close to, I mean, actually it's going to be a little bit less than 10. It's going to be like 9 point something, right? Not, yeah. So that's our, that's going to, and that, we would include that one though, wouldn't we? Everybody see that's a value that we would include. Because it could actually have that value, and that's the value it would have if this whole container were just a big sphere. Okay, give me 1 to 5. Is that making sense? How we got that? That to me, that's the trickiest part sometimes, is coming up with the domain. What are the values? I mean, where are we looking for critical numbers? Okay. So we got our domain. Good. Now what do we do? Yeah, just take derivatives. Right? And how would we do that? Well, we're going to leave, constant will just stay out front. Oops. Just leave that constant out front. What's the derivative of pi r squared? 2 pi r. And what's the derivative of 1,500 over r? Negative 1,500 r to the negative second, so over r squared. Good, right? We just treat it as 1,500 r to the negative 1, right? So we get that. Let's put the positive term first. We'll flip it around. Okay? Do we want to take a second derivative? Yeah, we should. So again, we get a positive constant out front. The derivative of 2 pi r is just 2 pi. The derivative of 1,500 over r squared is positive, right? Positive 3,000, because I'm going to have a negative, I have r to the negative 2 there. So it's going to make that term positive, and that's really what's important. So can you tell me, we don't need to know inflection points, but what's the sign of the second derivative going to be everywhere in our domain? It can be positive, isn't it? Right? So that's the main thing there. Okay, so now what? What do we have to do? Critical numbers, yeah. So the first derivative is undefined where? 0, but is 0 in our domain? No, it's not. And you can see it couldn't have been, right? There's another way we could look at that original function and say r can't be in the domain because there's an r in the denominator, right? Okay, but it would equal 0 when? say it again?
When the 2 pi r and the 15, when they equal each other.
Yeah, good. When those two terms are equal, that's going to be the condition when we're going to get a 0 value for our first derivative. Good. You guys are getting good at this. So C prime equals 0 when 2 pi r equals 1500 over r squared. So how would I solve that equation? Good. I just cross multiply, right? I've got a 1 on the bottom here, and I get 2 pi r cubed equals 1500. So then what? Divide by 2 pi, and then cube root. So r cubed equals 750 over pi. So r cubed, or so r would equal the cube root of that, 6.2, okay? Good, so we got our critical number, and then really all we have to do is just make a table, right? It's a pretty easy table. These tables end up being small. So if we make our table, we've got R's, cost, C prime, C double prime. Our domain goes from 0 up to, what was it, like 9.8, 9.85, is that what it was? Approximately. Our one critical number was at approximately 6.2. What was going on there? 0 first derivative. So what does that tell us? Well, I mean, if it's a 0 first derivative, that tells us one discrete piece of information. What is that? Horizontal tangent. Good. And we know we had a positive second derivative. So what's that tell us? Upward concavity, yeah. So we got a minimum, so that's our feature. This is a function that's continuous on its domain. If there's only one minimum, it's the minimum, right? Everybody get that? So that's our condition, that the x has to be 6.2. Now, what did they want us to tell them on this one? They wanted to know, find the dimensions that minimize cost. So we found x. How are we going to find r? Right there, right? We would just evaluate that function at, or sorry, we found r, didn't we? Sorry, we found r. We found r is about 6.2, so to find x, we would just plug 6.2 in that and see what the other dimension is. And that would be it. That would tell us. That's pretty cool that we can do that, right? And then that would be the exact dimensions of the container that would minimize cost while holding that volume. That's pretty incredible that we can do that, I think. I mean, hopefully you appreciate that. You would have no chance of even approaching being able to do that without calculus. Okay. That's probably good for one day? Okay.